Welcome to lecture 27. In this lecture, we'll study benchmarking real-time operating systems and real-time machines. So we have discussed a lot of operating systems. We have discussed many other real-time platforms as well. But how do we know that they're really working, right? So we need to benchmark them. So if you think of a typical sensor network node, so what are you going to have? You're going to have a small motherboard with with a limited number of sensors like a temperature sensor or a light sensor. So this is known and some communication capability. So this is known as a moat. So it will have a small CPU as well. So of course the CPU could be like a very simple 4 megahertz 8-bit CPU, right? An extremely simple CPU. And then it would have a small, communication antenna to communicate. And very little RAM, half KB of RAM, 1, 2, 3 KBs of RAM, and a very simple radio with a Bluetooth. So this would be a typical, real-time system or a moat that many people would be deploying. So if you see that nowadays pollution is a big issue, so it does make a lot of sense to have such kind of a moat developed and deployed in a wide variety of places to, let's say, collect pollution data and then transmit it to a central server. So here again, this would not require a lot of real-time involvement, but that said and done, we may, maybe put it on a moving bus or something where we are quickly moving through different areas of pollution and no pollution and so on. So then, of course, we would need some time guarantees. And then there are a bunch of other, applications of such pollution sensors as well, along with a bunch of other kinds of sensors, right? If you look at the entire spectrum of real-time operating systems and machines, they are also used in a large number of physical environments, such as chemical plants and nuclear plants, where of course the response times are much lower, but you will still have similar kind of hardware and you need to take a decision very quickly within a certain time bound. So our aim in this chapter is to devise tests, to devise metrics to see whether our operating systems are running within a real-time threshold or not. So the hardware is typically always simple, assembled off the shelf, right? So basically, the question is that what do you expect such hardware to be used for? So as I said, many of these embedded components can all be scattered all over into a network of sensors. Then they can either send all the information to a central point, but again, the central point may be far away. So they may be sending the information to each other, and then this could be a multi-hop network where that information is being sent to the central point, whatever is information. Pollution data, light, temperature doesn't matter, but typically such kind of a sensor network is formed. It's also called an ad hoc sensor network because the nodes may be moving and they may be creating a network differently, but that's the key idea. So in such kind of a scenario, the main aim is to ensure that we have real-time operation. So what are the software challenges? The software challenges are that we need to be power efficient with a small memory footprint, application specific. We will have multiple high rate data flows such as radio data, sensor data, and so on. And we need to provide a degree of real time a degree of real time performance. So, what we need is real time query, in a sense, sensing the physical environment and sending the data at real time feedback, sensing, and actuation. Given that we have limited memory for buffering, data has to be processed on the fly and sent. So let's now look at a very popular OS that is used in this category, known as the TinyOS. So the TinyOS is not a real-time OS, but still it is extremely popular. That is why it is entering our discussion. So in this case, given the fact that TinyOS is designed for also tiny hardware that has very little memory, there is almost no buffering in the radio hardware. If you miss a deadline, it also means that you lose the data. right? Um, so you don't provide hard real-time guarantees, but TinyOS still tries to remain real-time. But again, we'll not classify it as a real-time operating system. But we are starting this discussion with TinyOS to mainly understand what are the most popular solutions, right? So unfortunately, in many such cases, a real-time OS is not used, but instead OSs like TinyOS are used, which at best are soft real-time. So it is tailored to the requirements of a sensor network, and almost all of these OSs are event-driven architectures, as we have seen for ROS. In the sense, there is an event, you react to it, and then you keep quiet. Small memory footprint, very low overhead context switches, mostly FIFO scheduling, non-preemptible, and efficient resource utilization. When the job is done, you quickly put the processor to sleep. The architecture overview of TinyOS. So there is no kernel as such, in the sense everything is the kernel, right? So when you say no kernel, it means the applications and the kernel all put together, everything is the kernel. So you can directly manipulate the hardware. There is no process management because there is a single process. No virtual memory, one single address space. Memory is not allocated dynamically. We can't afford the complexity of a memory manager. There are no software signals or exceptions because there is no user kernel boundary anymore, right? So function calls are used. So the goal is to basically, on any such kind of a small sensor device, strip down the memory size as much and as far as possible and reduce the system overhead. So the overhead of OS is like this, that we have a graph of components, in the sense this software component invokes this invokes this, right? Something like this. And then we have a scheduler which, based on the precedence order, invokes the appropriate components via function calls, of course. So all of this is compiled into one executable. Then we have an event-driven architecture where, as I said, the moment some hardware generates some events, we work on it and then we sleep. There is a single stack without any user kernel differentiation. And the stack would include this, that we have our hardware abstraction layer. We have modules for actuating, right, for sensing and communication. These are the three main roles: actuating, sensing, and communication. Application with user components, and then again, as what sits at the top is a scheduler or dispatcher, which calls different parts of the application as per the rules that have been programmed. So if you look at TinyOS, it has a small memory footprint which is non-preemptible, very power efficient, efficient and modular, and an event-driven architecture, but it is not real-time, in the sense it doesn't support EDF or RMS, only FIFO. And if there is an overload, in the sense that if you have more tasks than what TinyOS can support, then there is no protection from at least a little bit of transient overload, which, as you saw earlier, most real-time scheduling algorithms actually provide. So now, we have looked at real-time operating systems, we have looked at TinyOS. So the question that arises is that if you are given an application and you are asked to select a computer system, how do you do that? So let's say you want to run a small web service, how do you do? So conventional CPU speed could be the millions of instructions you process per second, or the floating point operations you process per second. And then you could have peak MIPS and peak flops. These are good measures, but these are for traditional CPUs. They are not for real-time systems. You can also look at the peak processing speed, which many manufacturers are quoting. This is computed by considering the fastest instructions while ignoring other instructions. So this may not give you a very good idea of the spread of performance. You could write toy benchmarks or synthetic benchmarks, but toy benchmarks, so what many people would do is maybe write some basic algorithms like quicksort or merge sort, but the basic problem will remain. So even if you select a CPU based on a certain benchmark, the moment your actual application comes, the CPU may not perform that well. So, what could be a solution? You could analyze a very large number of practical programs, establish the distribution of different kinds of instructions, and then try to create a synthetic program. It may be meaningfully written, may not be meaningfully written in the sense it may be achieving something concrete or may not be achieving something concrete. But on the average, it can be made to capture the distributions of different types of instructions. But again, this entire discussion is assuming that it is only the instruction distribution that is responsible for the variation in performance, but that's not true. You also have memory behavior, cache hits, cache misses, and so on, which are actually a bigger reason for worry. So standard benchmarking programs, which are the Whetstone, Rhealstone, and LinPack, are basically for scientific computing. Spec is for CPUs. Parsec and Splash are for multi-core CPUs, and Rodinia is for GPUs. They are not really the most satisfactory for real-time systems. So nonetheless, let us look at a few of the standard benchmarking programs. So we have Spec. So Spec stands for the Standard Performance Evaluation Corporation. It's a non-profit organization. It creates CPU intensive benchmarks for evaluating processor performance. So we have had generations of Spec 89, 92, 95, 2000, 2006, 2017. So which are basically a bunch of programs to evaluate how good a CPU performs, right? CPU and its accompanying memory system. So you could have a financial, a stock market program, a chess program, an equation solver, an image manipulator. So all of these things are there within Spec. So a few of the Spec benchmarks are like this. We have Spec View Perf, which is a 3D graphics engine. For CAD CAM visualization, content creation, Spec JVM, Java engine, Spec JBB for server side Java, Spec Web, as the name suggests, it is for World Wide Web servers, dynamic content, and Spec Cloud. So let's look at our first metric, which is the Rhealstone metric, which is synthesized from the quantitative measurements of 7 components. I'll quickly list the 7 components. So the components are the task switching time. This is important. How much time elapses from one task switching to the other? The task preemption time, interrupt latency time, the semaphore shuffling time, right? So the time that you it goes in accessing semaphores, the deadlock breaking time in the sense you detect a deadlock, and how much time does it take to actually break the deadlock? Datagram throughput time. This is a network parameter, and the process dispatch time. You decide that a certain process needs to run. So how long does it take to actually run the process? So out of these 7 metrics, so you measure all 7 and then you create a metric out of them, like the Rhealstone metric. So let's take a look at the task switching time. Is the average time that the system takes to switch between two independent tasks, right? So you have task 1, you have task 2, right? And then the time it takes to switch between them, as we can see, which is this time over here. Task preemption time, on the other hand, is the average time it takes to transfer control from a low priority task to a high priority task, which basically means that a low priority task is running and then a high priority task arrives, right? So, given the fact that the high priority task arrives, how much time does it take to actually transfer control from the low to the high? So, we have to recognize an event that is causing a higher priority task to become ready, in the sense that higher priority task is becoming ready. The moment it becomes ready, we need to stop and preempt, right? And so, for that, we need to have a quick way, a quick data structure. So, recall, we have discussed this in the EDF and RMS chapters of how do we actually organize or manage or store the priorities of the tasks. So we need to access the priorities of the tasks and we need to take decisions accordingly, right? So this task preemption time would include everything, in the sense recognizing that A high priority task is coming, accessing the data structure for priorities and performing the switching. Then unbounded priority inversion prevention time is the worst case time delay between a high priority task's request for a semaphore and it actually getting it. So what will happen? So what will happen is that you could have unbounded priority inversion as we have seen, where multiple low priority tasks keep on executing because there is no priority inheritance. So this measures this time. So if it is not unbounded, the time will be low. Otherwise, it's going to be high, right? So it represents how effective is the priority inheritance mechanism of the mutual exclusion scheme. So again, unbounded priority inversion prevention time. So as you can see that T1 would acquire a resource, but given that T1 had the lowest priority, T2 and T3 will preempt it. And then T1 will release the resource, right? Ultimately, T1 will run, it will release, and T3 will get the resource. So this entire duration over here, right, T3 was waiting. So T3 requested the resource from here. So let's say T2 was executing, T3 ran here, so it requested the resource, but then it didn't get it because T1 was having it. So this entire time is what T3 is actually losing. Datagram throughput time is the number of kilobytes that one task can send to another task, right? So is the rate actually. So this measures the efficacy of all the common buffers in the kernel, which are used to transfer data between two RTO real-time tasks. So also, this could also indicate the time that goes from processing messages from the outside world and passing it to processes for processing, right? So this would also indicate the time that goes in the network stack. Process dispatch time. So processes do get activated by external events, right? So for example, let's say an interrupt comes or something, right? So TTPDL will be the interval between the time the system receives an interrupt request till the beginning of the task. So what would this exactly include? It would include the interrupt latency, the time it takes to recognize that the interrupt has come and to run the ISR. The ISR would execute and then there would be a context switch. So this would include all of that, which is basically the time it takes to dispatch a process because something has happened. Could be an internal event or could be an external event, doesn't matter. It would still comprise these three steps, and this will be the process dispatch time. So as you can see, the process dispatch time can be broken into three parts: the interrupt latency time, the interrupt routine, and the context switch time. So again, each of these can be broken down into multiple subparts. So the first one is of course the hardware delay, the time it takes to recognize that some interrupt line has been set to 1. T2 is the time that is required to finish the current instruction because only then you can flush the pipeline. And T3 is the additional latency required to actually load the interrupt subsystem. Once the interrupt subsystem within the hardware is loaded, T4 would indicate the pre-processing time, and then T5 will be the interrupt servicing time within the interrupt service routine, right? So basically the pre-processing would include some hardware time and some software time to basically store the registers in memory. And once all of that is done, the interrupt has been serviced. Post-processing, which is T6, would include basically scheduling the bottom half if there is a need, right? Or doing other kinds of bookkeeping and then coming back. So context switch is when we actually dispatch the process. So T7 is when you decide that you need a context switch and you know which process to run. And T8 is basically figuring out where the context of that process is stored, loading the context, populating the registers of the CPU and the flags, and restarting the process. So that is the context switch time in this case, which is T8. So these are the 8 different subcomponents of the process dispatch time. So the interrupt latency time is something that deserves some more consideration, right? So basically, we had seen this over here. So we are looking at it in slightly more detail. So the interrupt latency time would be the time from when the CPU receives an interrupt request until this point that the interrupt routine actually starts running, right? Till the first instruction of the ISR. So from, let's say, a task stopping because you got an interrupt to the running of the ISR is basically this would be the time that we are talking about. So what would it consist of? As we have seen, the 3 components of the hardware delay and the time to finish the current instruction, because it has to get out of the pipeline, and other hardware latencies that are involved. So the hardware delay would be the time required to notify the OS, right? And the latency time would be the time required to prepare the system for the execution of the ISR, which basically means loading the interrupt service table from the OS, looking up the number of the interrupt, right? So it'll basically be a lookup operation, getting the PC and loading the code of the interrupt service routine into the caches, right? Or at least into the memory. So this was the Rhealstone metric, which had bunch of 7 parameters, and then you look at the basket of 7 parameters and you basically compute a metric. So this is kind of a subset of what you could actually do for benchmarking. So there are a bunch of RTOS services that could be benchmarked. So one is that the context switching time in different kinds of scenarios, right? So in scenarios where we are looking at a non-preemptive setup, also called a cooperative setup, preemptive context switching, interrupt processing with and without preemption, message passing. So this will mainly be message passing between different processes on the same hardware. Semaphore processing and memory allocation deallocation. So mind you, the rest all was there in the Rhealstone metric. This was not there. This is new, right? So we could create important features and look at a tridimensional measure, which would include the CPU speed. So in this case, we are trying to kind of look at the full system. So the CPU speed would be the millions of instructions per second, and then the number of interrupts we can process per second, which would be like MIPS2, in the sense that what is your interrupt processing throughput, and the IO throughput, in the sense how many IO devices you can process. So again, some may argue that there could be an overlap between these two, but again, IO of course does generate interrupts, but it's more than that. It also comes with its own data which needs to be kept somewhere and transferred to the memory using DMA. So those issues are also there. So we can compute the product of all these three suitably normalized M1 times M2 times M3, and then call this the volume, and then they take the cube root of that and call it the measure. So this is known as a tridimensional measure that includes the RTOS aspect over here as interrupts, the CPU aspect and the IO aspect. So the interrupt processing overhead defines how long it takes to complete an application with a specific interrupt injection rate. Basically, it means that if I have n interrupts, this is my time, minus T0 when I have no interrupts, divided by the baseline, which is T0, multiplied with 100. So if T0 is 1 second, this is 1.6 seconds, then this will be 1.6 minus 1 divided by 1, which is 60%. Then let's look at real-time OS benchmarks. So we have two categories of benchmarks which we consider to be important. We could have deterministic benchmarks and latency benchmarks. So the subsequent slides will talk about them. Deterministic benchmarks measure the determinism, or how well you can predict the latency, throughput, etc. of OS services. That would include the jitter of, let's say, the built-in timer, right? So the timer would include both hardware as well as software components. What is the response time of different OS modules? And bin time. So we will discuss bin time in great detail. Kindly hang on for some time, right, till we come to bin time, but it's mainly timer jitter response and this funny thing that we have not seen before called bin time. So deterministic benchmarks would be like this, that we have discussed the three components, 1, 2, and 3. Bin time is defined here. We'll come to it. So timer jitter basically means you create a periodic timer, which periodically, let's say, gives an interrupt, and you measure the deviation between the desired time of the timer and when it actually expires. So what you will see is that, of course, you would need a separate accurate clock that runs externally for this purpose. But this will give you an idea of the response time of the operating system and how well it can respond to these periodic timer events. So the timer period will be between 1, 10, and 100 milliseconds for such tests. But that will essentially give you an idea that is the operating system free enough to take up a timer interrupt immediately, or is it busy doing something else? So this will tell you, is it overloaded, or for a normal load is it being able to process it or not. Response is like this, that you execute a fixed processing load and you just measure the execution time repeatedly over multiple runs. So that will give you an idea of whether the execution time of a program is predictable or not. In a sense, if it is not predictable, then across different runs you will actually see different execution times that may vary widely. So that is of course a bad thing for a real-time operating system. But of course, if you run it 100 times, we can plot the distribution and figure out how bad is it. Could be a simple thing like adding numbers or copying data from one place to the other, or could be complicated as well. Bin time. So in this case, you call a time of day clock, in the sense you call a clock to figure out what is the time and measure the intervals between the calls, right? So in this case, what you do is that you are basically measuring the time that it takes to perform a system call, right? So what is the system call over here? So the time of day that an application is trying to query is nothing but a system call, right? So you are sending a get time system call to the kernel. The kernel will respond with the time. So mind you, whenever you give a chance to the kernel is kind of opportunistic, right? So it will always take the chance to do some of its own work, execute some of its own code, which is not something to your liking, but this is something that the kernel will do, and this can cause a jitter. So if you, let's say, call the time of day clock repeatedly where the interval is known, or you are measuring it with a separate external clock, you can figure out how much is the kernel blocking you, in the sense how much of its own work is it scheduling, and how much of jitter is that causing from an application standpoint, right? So you can think of this as more as the system call response, right? So this can be called as a syscall response broadly. It's a proxy for that. Whereas response is like a full system response, right? So the response over here is pretty much for the full system, the entire system. And the timer jitter is again looking at the interrupt response time, right? So basically, if you think of it, we are measuring three very different things here. Timer jitter is the interrupt response time, or rather the jitter in the interrupt response time. The full system response is something slightly different, right? And that's for the entire system. And bin time is exclusively for system calls, of course, measured in a very simple manner. So if we look at typical timing devices, so stopwatches would have a resolution of, let's say, 10 milliseconds, and gradually the resolutions for others would keep going down, in the sense the basic clock, system clock, 15 to 30 milliseconds, and any kind of a software clock where you would measure time by running instructions or something, that would be at the level of microseconds. But of course, these timer chips, right, are the most accurate devices which are available to current CPUs, that can roughly give you a 1 microsecond granularity. Of course, something lower you need, real hardware and logic and bus analyzers and so on, but we are not even looking at that. So what we are looking at this is to include high resolution timers, which is definitely doable, or use proxy software clocks where you have a thread that is just, calling a for loop, and based on how far it has gone, you can get an idea. So if that thread is not being swapped out, this can give you a reasonably good idea of how long it is taking. For Prof and GIF and other profiling things using basic system calls and so on are well not very accurate. Their accuracy would lie somewhere in this region, which depending upon the application may be suitable for you, may not be suitable for you. Now let's come to the testing time jitter. So most current CPUs, as you have seen, would include a timestamp counter, which is updated either on every CPU cycle or on every CPU jiffy, where a jiffy is a periodic timer interrupt which is generated, let's say 1 millisecond, once every 1 millisecond on a current system. So POSIX provides the clock get time call. It uses this timestamp counter to give a reasonably high precision time of day clock, okay, reasonably high precision. So now coming to the response measure, right? So this was the timer jitter, of course, over here. The response measure is the actual execution time for a large block of processing, let's say 10 milliseconds or more. So that will tell you whether the system is deterministic or not, right? So what you do is that you take a bunch of runs, 10 runs, 20 runs, 50 runs, and calculate the deviation or the distribution of the actual execution time. That will tell you that how bad are things from a real time perspective. If let's say the system is very well behaved, the graph would be something like this, otherwise it will be something like that. So what do you need to do? Nothing much. Write a dummy program that is accessing, stressing all parts of the system. Could be arithmetic operations, for instance. Could be memory operations, for instance. Doesn't matter. You stress different aspects of the system. And the synthetic whetstone benchmark does that. And then you just run it many, 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 many times. The distribution will give you the information that you need. So the time required by each call, right, would consist of the system call time, the time spent in the mode change, the time that the kernel takes, the time that the application takes. So given it, the fact that it's a full system, it would actually consist of a bunch of measures. Now let's come to bin time. So bin time is something that was specific to system calls. So one thing you need to keep in mind, the different measures that are being suggested are not necessarily mutually exclusive. So they're not. But that's okay. Insofar as benchmarking is concerned, mutual exclusiveness is not a criteria that's very much in demand, even though if it's desirable that there is some degree of mutual exclusivity. So this basically for a given system call is measuring the distribution, which of course in our small example was to get the time of the day. So it will give a good indication of the maximum time that is spent in the kernel, which basically means I go for the kernel, but the kernel, given the fact that it has gotten a chance, does more work of its own and then it comes back. So the in a high priority real time thread, if I repeatedly call the time of day, I can get the response time for each call, and that will tell me that what is the kernel's response for me, right? So it will indicate the time for which interrupts are blocked and also opportunistic execution is happening. So we have finished deterministic executions. If you look at it, how did we come here? Well, we looked at the Rhealstone benchmarks. Then we looked at the tridimensional measure, right? Which of course had multiple things: CPU throughput, interrupt throughput, and IO throughput, right? Tridimensional measure, which had the CPU, IO, and interrupts. And then we are looking at here two kinds of benchmarks: deterministic and latency benchmarks. Deterministic benchmarks further we divided into different categories. So one was to measure timer jitter, which is basically nothing but to measure interrupt response. Then, of course, what we call response, which is a full system response, includes a whole bunch of components. And then what we call bin time, which is nothing but the system call response, right? So basically, these all comprised a deterministic benchmark. So of course, we are now looking more at generic general purpose benchmarks. So what we should now look at is the second category, which are the latency benchmarks to be described in this slide. So latency benchmarks will be like this. So one benchmark is sync. So this measures the latency of a thread to thread or process to process synchronization, right? So latency benchmarks, unlike the previous category of deterministic benchmarks, which are based on multiple runs and kind of computing a distribution, here you measure a specific aspect, like the context switch time between threads or processes when they are synchronizing, right, at a semaphore, for instance. Then we look at message passing, which measures the latency of sending a message from thread A to thread B or process A to process B. So that can also give you an indication of the possible throughput, and it is parameterized by the buffer size, right? So how much buffer space do we allocate? Then let's say one process, which could be the kernel, is sending a message to another process, which is not really a message, but it's actually a signal, right? So as we have said, interrupts and signals are kind of contrasting mechanisms. So what happens is that fundamentally, be it an interrupt or a system call or an exception, goes from the application to the kernel. But when the kernel wants to notify the application, it actually sends a signal. It's in the reverse direction. So this has been slightly generalized in the sense process A can now send a signal to process B in real time, known as a real time signal, which measures the latency of the real time signals between the two processes. Right. So this is again one more measure. So these three measures will comprise broadly what you speak of a latency benchmark. So different synchronization tests can be done. You can do a latency of a single system call. It could be the latency of a round trip signaling in the sense signal, wait, then signal, and then wait. So this latency could be measured. If a low priority task is being delayed by a medium priority task, so you could look at the delay and then you could see that. So this is actually, kind of simulating an unbounded priority inversion case where a low priority task is being swapped out by a medium priority task, and then the high priority task has to wait because the low priority task A has basically grabbed onto a resource. So even this can be measured. So all of these things, right, all of these interactions, which is a single system call or a signal wait kind of synchronization or a resource based synchronization, will all come in the synchronization latency test. So then we can, of course, create many other kinds of tests. So basically, for synchronization, we can create a signal wait semaphore kind of thing. Then the semaphores can be used to send signals between threads or processes. So then we can also use this to assess what is an OS's ability to deal with priority inversion, right? Particularly unbounded priority inversion. And if a priority inversion occurs, we can quantify for how long does it occur, right? And if the priority inversions do not occur, then this also can be seen. So now let's conclude, right? So the primary means by which an operating system tries to meet all the task constraints is basically task scheduling. So this has been our main workhorse up till now. Traditional operating systems such as Unix and Windows are very satisfactory for real-time applications. Embedded RTOSs are in general light and reconfigurable, right? And some benchmarking can be carried out, or in my opinion, if you would allow me to add my opinion, it should be carried out to compare RTOS realistic performance, right? So this is something that should be done. So this finishes our complete discussion on RTOSs and benchmarking. So now in this course, 3 lectures are left on real-time communication and real-time databases.